Okay, so question number 2. State two typical chemical properties of transition elements. So if we talk about the typical chemical properties, that the one which you have been studying since your O levels or IGCSE, that uh, they have variable oxidation state. Then another one, that they act as a catalyst. Beside this, you can also write that they form complex ions, that is also their chemical properties. Or you can write that they form colored compounds, so that is also their chemical property. Okay, now aqueous solutions of cobalt 2 salts containing the complex ion. Okay, they have given you the complex ion. Now they ask you to define complex ion. So we can state its definition like it's a ion in which central metal atom is surrounded, or instead you can write natively bonded with ligands. Is this understandable to all of you? Now, 2B2, the sample of hexaaqua cobalt 2 ion are reacted separately with an excess of aqueous ammonia, with an excess of concentrated hydrochloric acid, and with an excess of sodium hydroxide as shown in figure. So if you recall, when it is reacted with excess of aqueous ammonia in cobalt, all of the water are displaced by the ammonia ligand and forming 6 hexaamine cobalt 2 ion. And when it reacts with the sodium hydroxide excess, only 2 of the water ligands are displaced by the hydroxide and 4 of the water ligands stay intact. And as 2 hydroxides are bonded, each one have a -1 charge, making -2. So cobalt neutralized by that one, and the net charge over here would be 0. But as here ammonia is a neutral, so that's why the whole ligand or whole complex basically carry 2 positive charge. And in the second reaction with the aqueous ammonia, the complex carried no charge because hydroxide is -1 and there are 2 hydroxide, which makes it -2, and 2 cobalt plus, and the cobalt have a +2, so the net charge would be 0. Okay. Now, if you recall, when we react with the hydrogen hydrochloric acid, chloride act as a ligand, and when chloride act as a ligand, so all of the you know uh, water are replaced by 4 chloride ions. So each chloride has a -1 charge. So 4 chloride has -4 charge, and cobalt has oxidation number of +2. So +2 and -4 makes it -2. So the net charge would be -2 over here. Is this clear to all of you? Okay. Now, complete the table 2.1 about the reactions shown by cobalt, hexaqua cobalt 2 ion. Okay. So we have already figured out the formulas. So we have to write the formulas, we have to write color and state and the type of reaction. So if you recall this, it's meant over here. So the complex ion would be this over here. In with HCl, the complex ion is COCl4 with a 2 negative charge, and with sodium hydroxide, it's cobalt. The complex ion has 2 hydroxide and 4 water molecules as a ligand. Okay. Now, they are asking for the colors of the solution. So if you recall that when the amine is a ligand with the cobalt, it will form brown solution. And with the chloride, there is a blue solution. And with the hydroxide, if I recall, it's pink precipitate or blue precipitate. Okay, let me check. I have shared the notes with you guys, so you can go through those notes to find these colors in the transition metal. If you will find the file over here about transition metals. Yeah, here we have. It's the reaction of copper. Okay. So see the brown solution, the blue solution, and okay, let me add it over here. Okay, it's not mentioned over there. Let me write it over here. That if there is a cobalt hexaqua ion, it reacts with sodium hydroxide, so it reacts with 2 moles of sodium hydroxide forming. And yeah, it's a blue precipitate, it's not, pink. 2 positive and 2 of the water molecules are released, and it's a solid. It's water insoluble. As see, it's water insoluble over here as well. With the copper, we get a blue precipitate. Here also we get a blue precipitate. Okay. So you guys just take the screenshot of this. Can anyone take the screenshot of this and share it in? Yes, please. Can anyone do take the screenshot? Okay. So yeah, blue precipitate. Okay. Now the reaction, as you see, it's a solution. So initially the solution, when adding aqueous ammonia, the solution is, we get the solution, there is a no precipitation or no solid formation. So we call the reaction ligand exchange. That same goes with the second reaction with the hydrochloric acid, as no precipitate will form. Only it's the solution, only the color is changed. So we say this reaction is also a ligand exchange reaction. Now, third one, where there we are observing the precipitate, so we will write over here precipitation. The type of reaction is precipitation. Is this clear to all of you? If any one of you has any query, any question regarding this, please ask. The ethane diode ions with the formula C2O4 2 negative can act as a bidentate ligand. Okay. Explain what is meant by a bidentate ligand. So because in the third one there is a precipitates. If the if it's not solid, Alina, if it's a aqueous only, then it's also a ligand exchange. As there are precipitates are formed, so that's why we call it precipitation reaction. Yes, Mariam, which charges you are talking about? The charges on the complexes. So it's very easy. If you see over here, it is a 2 positive charge, right, Mariam? And if you recall water, do water have some charge? Water is always zero, isn't it? So it means this 2 positive is due to the cobalt only. So if you look at ammonia, ammonia is a molecule, its oxidation number is 0. So there are 6 ammonia, so it is 0. So cobalt is a 2 positive, so that's why we get the whole charge 2 positive. Is it clear? Okay. Now have a look over here. As chloride comes, so in HCl, the chloride has a -1 oxidation state, isn't it? So there are 4 chlorides, which means -1 times 4, which makes it -4, right? And we know that cobalt is +1. So +2. So +2 and -4, we got -2, and that's why I put a charge -2 over here. Is this clear? Now, if you look over here, there are 2 hydroxides. So hydroxide is -1, and there are 2 hydroxide, which makes it -2. Water is 0, and we know from the first complex that the cobalt is +2. So +2 and -2 makes the whole charge 0. So that's why I didn't put our charge over here. Is it clear? Good. Now, so a ligand is the one which forms a dative bond. And if we are saying bidentate, it means the ligand which forms 2 dative bonds. And how it forms 2 dative bonds? By donating 2 pair of electrons, or by using 2 pair of electrons. So I can write it is a species which uses 2 lone pair of electrons to form 2 dative bonds. Is this clear to all of you? Now, the complex, this is the formula, exists as a stereoisomer. Complete the 3-dimensional diagrams in figure 2.2 to show 4 stereoisomers. C2O4 negative ligand is represented by using this. So see, there are 2 oxygens. So it is the one which is a bidentate. This one is a bidentate. See, they have drawn it over here. We have to make the write the other ones. Put the other ones to show 4 uh, stereoisomers. Okay. So see, there are 2 same ligands which are water. So what I can do first, that I put the 2 water at 180 degrees to each other, and then put a chlorine and bromine 90 degrees to each other, forming one stereoisomer. Now, in the other one, what I can do, I put both the waters small ligands at to 90 degree, and then put these 2 over here. Is this understandable? Now we have to show two more. So what we can do, we can do change the positions of the water molecules beside these two, the other possibilities to show three more isomers. Oh, sorry, to show two more isomers. So I can do, for example, if I put one water over here and one water over here, and then put the chlorine and bromine like this. And then, for example, if I keep the water over here and the other water moves to the this position and shifts the bromine from here. So this would be the fourth isomer. So that's how by shifting the, by changing the, by swapping the position, you can make the rest of the isomers. Now, in the next part, state the oxidation state of cobalt in this complex and type of a stereoisomerism shown. So the type of a stereoisomerism is cis and trans, because the water is at 180 degree and then 90 degree. So you can either write cis and trans or either you can write geometrical. Okay. Then you have to figure out the oxidation number or the oxidation state of cobalt. So see, what is the net charge on it? It's -1. Chlorine is -1, bromine is -1. If you see C2O4, they have given you over here. Otherwise, you have to remember it. I have mentioned in the notes. It's -2. And water is, we know, 0. So what would be on cobalt? What charge will be on cobalt when we all add all of them? We will get a -1 charge over here. Yes, can anyone tell me the oxidation number over on cobalt? Then when we add all of these values, we get an answer of -1. What will be the number? What will be the number present on cobalt? Yes, who is going to tell me? Yes, Mariam, can you tell me? Yes, Bahish, Ahmed, Nuria, anyone? You see, it's simple mathematics. You have to add all of the values and you have to see, figure out this number. Yes, very good, Vash. It's going to be +3. If you add them, see, plus -2, -1, and -1 makes it -4. So obviously it is going to be +3. That's why you are going to get the -1. So it's +3. Very good, Vash. So the oxidation state of cobalt is +3. Now, question number 3A, complete table 3.1 by placing one tick in each row to indicate the sign of each type of energy changes under standard conditions. Okay, bond energy. Yes, bond energy is what? It is the energy needed to break the bond. So what it is going to be, positive, negative, or either? Yes, if you need to break the bond, the energy is needed, or yeah, very good, Mariam. It's positive. It's always positive. So because to break the bond, we always need the energy. Enthalpy change of atomization, it means to form 1 mole of gaseous atoms from the element. So when we from the element, when we making the gaseous atom, the bonds are broken. So it is going to be positive, negative, or either. It is also going to be positive only because it's the energy change to make 1 mole of gaseous atom, and gaseous atom is made from the elements, so the bonds are needed to be broken. Now the enthalpy change of formation. So if you recall the enthalpy change of formation, it's the formation 1 mole of a compound is being formed from elements, so bonds are broken and bonds are formed. So it depends where the energy is needed is more. In bond breaking, the energy that is needed is greater, or when the bonds are formed, the energy that is released is greater. So it can be either negative or positive. Is this clear to all of you? Now, after this, in the next part, define standard enthalpy change of atomization. So you guys must remember the definition that it is the enthalpy change when 1 mole of gaseous atoms are formed from elements under standard conditions. Okay. So the definitions you guys need to memorize them, remember them. Table 3.2 shows some energy changes. Okay. So here we got some energy changes. Standard enthalpy change of atomization of silver. It means that it is solid silver to gaseous silver. First ionization energy of silver. It means when gaseous silver atom forms gaseous silver 1 plus ion. Second ionization energy of silver. It means that gaseous silver ion with a maximum charge turns into 2 positive charged gaseous silver ion. Bond energy of oxygen, double bond oxygen. So it means when this molecule having a double bond breaks the energy and turn into 2 oxygen atom. And here oxygen single bond. So it means when this atom turns into this 2 atoms are bonded atoms turns into 2 single atoms. Okay. Then first electron affinity of oxygen. So it means when the gaseous oxygen atom gains 1 electron and turn into gaseous -1 ion. Second electron affinity of oxygen. It means when gaseous oxygen -1 ion gains 1 electron and forms gaseous 2 minus ion. First ionization energy of oxygen. So it means when oxygen turns into oxygen atom in a gaseous state, its 1 mole turns into +1 ion. Standard enthalpy change of silver oxide. So it means when 1 mole of silver ion and 2 moles of silver ion and half mole of oxygen, 1 mole of silver, 2 moles of silver atoms and half mole of oxygen gas molecule reacts to form 1 mole of silver oxide. So that is this. Okay. Now what they are saying, calculate the lattice energy of Ag2O silver oxide using the relevant data from table 3.2. It may be helpful to draw a labeled energy cycle, show your voltage. Okay, here, if you recall the formula was if you have to find the lattice energy the lattice energy is equals to enthalpy change of formation minus sum of ionization energies, because they are silver and oxygen, so we need the sum of atomization and sum of ionization energies and sum of electron affinities. So if you work on this formula, it's Ag2O. So it has silver ions and basically two silver ions and one oxide ion. So from here you get to know what you need. You need twice of atomization, of silver and twice of first ionization energy of silver, because there are two units. You need only the atomization of oxygen because it's a 1 mole, and you need first electron affinity and sum of first and second electron affinities for oxygen. Is this understandable to all of you? You need for silver, you need this, for oxygen, you need this. And another important thing, if you guys recall, that atomization is equals to bond energy divided by 2, and it's for diatomic elements like oxygen, it's an O2, right? Oxygen is O2, which means oxygen has a double bond between two oxygen atoms. Till here, is this clear? So we figure out what data we need. Now we have to put these data in the equation, in the expression. So the enthalpy change of formation. So see, we need the enthalpy change of formation, this one. Then what we need the twice of atomization of silver. So here is the atomization of silver and we need it twice. What we need? Twice of first ionization energy of silver. So that is the first ionization energy of silver and we need it twice. So see, to confuse you, they have given you the second ionization energy, but silver is in +1 oxidation state, so we don't need it. So that is not needed. Okay, bond energy of O2. So we need this one, but it's a bond energy when, see, 2 moles of oxygen atoms are forming, and as we have discussed, we have to divide it by 2. Okay, so we have to divide it by 2. So we don't know this. In oxygen, there is no single bond, so we don't know this. So to confuse this, they have given you this. First electron affinity of oxygen, yes, that is needed. Second electron affinity is there, yes, it is needed. First ionization of energy of oxygen. So oxygen is +1. So in the compound, the oxygen is not +1, so it's not needed. So see, that's how you will work out and figure out which values are needed and which values are not. Now you are going to put these values over here. So the formation is -31, right? So I'm going to put -31 over here. Then minus, I need twice of atomization of silver. So 2 times 285. Then I need atomization of oxygen, which is equals to its bond energy divided by 2. So it's 496 divided by 2 over here. I am done with this one. I am done with this one. So plus 496 divided by 2. Now we are done with the atomizations. Now for ionization energy. So it's silver and it's +1 ion. So just we need this one because there are 2 silver atoms. So 731 times 2. So 2 times 731. Now sum of electron affinities. So there are two electron affinities because oxygen is turning into -2. So -141 and plus 798. So -141 and plus 798. So here we got the whole expression. Now you have to solve it in the calculator and you will get the answer. Is this understandable to all of you? So we put it these, we put it these. Now can anyone calculate it for me and tell me the answer, please? Very good, Maria. So the answer is, can anyone cross check the calculation? It's minus 2,968 kilojoule per mole. Yes, is this clear to all of you? So I'm going to write over here minus 2,968. Okay, now next part. So it is the trend in the magnitude of lattice energy of silver compounds. Okay, Ag2S, Ag2O, and Ag2Se. Now have a look over here in the periodic table. The periodic table is provided to you. If you see in the periodic table in group 16, you will find oxygen over here, then you will find sulfur over here. And what I remember that beneath sulfur, there is a selenium. Not sure. So yeah, it's selenium. So oxygen, sulfur, and selenium. So selenium is over here. So and all of them are group 16 compounds. So all of them have a -2 charge, right? So it means that if the oxide ion has this much size, then sulfide ion has this much size, and then selenide ion has this much size. So the -2 charge remains the same, but the size is getting greater, is increasing. So it means when we move down the group, the density, the charge density, what happens to the charge density as we move down from oxide to sulfide to selenium, the charge density decreases. And as the charge density decreases, it means, just please give me a minute. Sorry, please give me 1 minute. Okay. So yes, what happens to the charge density? Charge density decreases, and as the charge density decreases, so what happens to the attraction? Attraction decreases, and as the attraction decreases, it means that the lattice energy decreases. Is this understandable to all of you? So which one is going to be the least exothermic among these three? Ag2, Se, silver selenide, then silver sulfide, then silver oxide. So that's what we are going to write. That's what I have discussed. That the size of anion decreases from oxide to, sorry, we am talking about decreases. So sulfide to selenide to sulfide to oxide. Hence, the charge density increases in a order. So I'm going to write the opposite order of this one. Increases in order. Selenide to sulfide to oxide. Hence, we can write so the attractive forces increases. So more stronger the bond, the more exothermic it is, right? So the attractive forces increases in order from selenide to sulfide to oxide, or you can write in exactly the reverse argument. Is this clear to all of you? Yes, if any one of you has any confusion in this, please ask. Okay. Yes. Till here, is this clear to all of you? Okay, so I'm ending the class over here, and tomorrow from here onwards we will be continuing. Yeah, greater charge density makes it stronger to bond. The bond is stronger, the forces of attraction is stronger, and as a result, when the forces of attraction is stronger, when the bonds form, the more energy is released, so it becomes more exothermic. The lesser the charge density makes the forces of attraction weaker. So the bond, when the attraction develops, the attraction are weaker, so the less energy is going to be released. So it's less exothermic. Yes, Alina, is this clear? Okay, so from here onward, we will continue in our next class tomorrow. So see you everyone tomorrow. Take care. Goodbye and Allah Hafiz.